Our today's topic is Maxwell Boltzman distribution function. Before directly jumping to the topic, let's have some concepts beforehand. Let's assume I have three particles A, B and C and I have to arrange them in three energy states. So how many ways I can arrange these three particles in three energy states? I can keep A here and B, C here. I can keep A here, C here, B here, and then let's put B here. For the next two arrangements, let's put B here. So A, C and C, A. Next, let's put C here. So that will be A, B. Again C here, it will be B, A. So in total, I can find 1, 2, 3, 4, 5, 6. So total, there are 6 number of ways to arrange three particles A, B, C in three energy state. That means I can arrange three particles in three energy state by 3 factorial ways, right? Because 3 factorial means 3 into 2 into 1, that is 6. And I must say that here the particles are interacting. So when there will be repetition, what will happen? Let's say I have to arrange A, B. Now there are repetition. How many repetitions are there? There are 2 repetitions, because one particle is repeated 2 times, so there are 2 repetitions. And now again I have to arrange them in 3 energy states. So A, B, A, and again B, A. So maximum I can find 3 number of ways to arrange these 3 particles in 3 energy state. That means now I have 3 factorial divided by number of repetition is 2 factorial into 3 minus 2 factorial, that is 3 ways. So when the particles were different, that is A, B, C, there were no repetition, I can arrange them in 6 number of ways in 3 energy state. But when there are repetition, then there are only 3 meaningful arrangement or 3 number of ways to arrange them in 3 energy state. So this concept I will apply the same thing while discussing the Maxwell Boltzman distribution. Now what will happen if the particles are not interacting, that is for non-interacting particles? Let's say I have 6 energy state, 1, 2, 3, 4, 5, 6, and I have 5 particles A, B, C, D, E. So how many ways I can arrange A in these 6 energy state? I can put A here, here also, here also, here also, and in this 2 also. So there are, that is 1, 2, 3, 4, 5, 6. So to arrange A, how many ways are there to arrange A? So there are 6 ways. Now as the particles are non-interacting, I can put B in any of this energy state. In this case, in this previous case, particles are interacting, but here particles are non-interacting. So as they are non-interacting, I can put B here also, and on these states already they are like empty, I can put B there also. So to arrange B, there are 6 ways also. And again, as the particles are non-interacting, I can put C here also, here also, so there will be no issue. So to arrange C, there are total 6 ways. So just like this, for D and E also there are 6 ways. So how many total ways are there to arrange these 5 particles? That is 6 into 6 into this 3, 6. That means I have 6 to the power 5 ways to arrange these 5 particles in this 6 energy state when the particles are non-interacting. These two concepts, that is this repetition and this thing in mathematical, we know this as 3C2. 3C2 means 3 factorial by 2 factorial into 3 minus 2 factorial, right? So these two concepts I will apply while discussing Maxwell Boltzman distribution function. So now let's start Maxwell Boltzman distribution. Okay, so what is our task? Let's first discuss what we have to do in this distribution. Let's assume that in a system I have total n number of particles, and in this n number of particles, n1 particles are of same kinds. So there are n1 particles, like they are same type of particle. So n1 particles of first kind, there are n2 particles of second kind, and similarly there are, let's say, nk particles of, let's say, kth kind. So I have, in total I have n particles, and among these n particles, n1 particle is of first kind, n2 is second kind, and nk is kth kind. That means, let's say, I have 1000 particles. Among these 1000 particles, 100 particles are of first kind, that is, they are of same type. Then there are, let's say, 50 particles of second kind, and let's say then 200 particles of third kind. Let's say then what will be the left and for the kth kind. So that is how I am dividing the particles. Total is 1000. Among 1000, 100 is of first kind, 50 is of second kind, 200 is of third kind, and so on. Similarly, among n particles, I have n1 particles of first kind, n2 particles of second kind, and nk particles of the kth kind. Now I have to arrange them in energy cells, or let's say in energy boxes. Let's say energy of the first box is epsilon 1. So this is the first box having energy epsilon 1. Then there will be a second box having energy epsilon 2, and there will be boxes like this, and the last one will be, of course, having energy epsilon k. So I have energies epsilon 1, epsilon 2, ... epsilon k. And this epsilon 1, this box is subdivided into G1 parts, that is, G1 is its degeneracy, G2 is its degeneracy, and similarly Gk is the degeneracy of this box. What do I mean by degeneracy? Degeneracy means simply same energy but different level. Suppose, for example, let's talk about, suppose we have a energy cells, and if we look into it with a spectrometer of high resolution, we may find that this energy state, it's not a single energy state, it is subdivided in in 3 parts. That means, let's say the energy of this energy state is E1 electron volt, then these three energy of these three will be E1 electron volt, E1 electron volt, E1 EV. So these three will have same energy. So degeneracy concept is somewhat like this, that is different states but same energy. So the energy of this box is epsilon 1, and there are G1, it is degeneracy, means there will be G1 number of cells. So ... there will be total G1 cells, and all these lines, that is all this level, they will have epsilon 1 energy. And in this box also, then it is having degeneracy G2, say it will have G2 cells, and all they will have epsilon energy epsilon 2. And in this case also its degeneracy is Gk. So I think this concept is clear. If not clear, you can comment. I'll make another video on this, on degeneracy. Now our task is to arrange n1 particles. So n1 particles, I have to take n1 particles from where? From n particles. Like suppose this is a box, there are many red balls, green balls, and let's say blue balls, and there are, let's say, black balls also, and let's say there are red ball also. So it's like I have to arrange all the red balls. So the red balls are of first kind, or the just like I told, n1 particles of first kind. So the red balls are of first kind, and I have to arrange them in this box. That is, I have to arrange n1 particles in the first box, then n2 particles I have to arrange the blue balls in this box, and then I have to arrange the black balls in this kth cell, So I have to arrange nk particles in this kth cell. So what is our goal in Maxwell Boltzman distribution? I am repeating our goal. This is our system, and in this system we have total n particles, and I have subdivided these n particles in n1 particles of first kind. That means let's assume the red balls, they are of same kind. Then n2 particles of second kind, let's say the blue balls, they are of second kind, and last the nk particles of kth kind, these are the black balls. And what I am doing is I am arranging them. So I am arranging n1 particles from n particles in their first cell, the first cell having energy epsilon 1 and degeneracy g1. Next I am arranging n2 particles of second kind from n particles, that is I am arranging the blue balls from n total number of balls in the second box, having energy epsilon 2 and degeneracy g2. So this is our goal. This is our first goal. So our first goal is clear. Okay, so now I have taken n1 balls or n1 particles from these n particles, and I have arranged them in this box, right? Now as there are g1 sublevels, so when the first arrangement is done, now our task will be to arrange those n1 particles in these g1 levels. So first goal was to arrange n1 n2 nk particles of same kind to arrange in epsilon 1 box, epsilon 2 box, epsilon k box. That was our first goal. Now when the first work is done, next what will be our task? Now I have n1 particles to distribute in this box. So now I have to distribute or arrange these n1 particles in G1 cells. So that will be our two tasks in Maxwell Boltzman distribution. And the total, and if I like take multiplication of these two, that will be simply our Maxwell Boltzman distribution. So now let's do it. So how I can arrange n1 particles from n particles in this epsilon 1 level? So it will be n factorial. So total there are n particles, so n factorial is the arrangement of n particles. Now I wish to take n1 from n, then it will be n minus n1 factorial, because when I have arranged n particles, when I took n particles, n1 particles is already inside them. So that means now this is the repetition, just like in this case 3 factorial divided by 3 minus 2. So 2 was the number of repetition. So here number of repetition is n1. So n factorial by n minus n1 factorial into simply n1 factorial. So in just like in this case 3 factorial by number of repetition, and then 3 minus 2 it was. So in this case also this will be the number of meaningful ways of putting n1 particles from n particles in this first box. So that is simply NCN1, right? This is NCN1. So this is n factorial by n minus n1 factorial into n1 factorial. Now how many? Now okay, the first box is done. Now I have to arrange n2 particles here. But how many particles I am left with? N minus n1 particles I am left with. So the next case will be n minus n1 factorial, that is I am left with, and our goal is to take n2 particles from this n minus n1 and to arrange them in this box. So that will be n minus n1 minus n2 factorial into n2 factorial, and this will be n minus n1 C n2. So and then the next task will be remaining, how many particles are there? N minus n1 minus n2 sorry. So to arrange So these number of particles I am left with. So in the third case I have to take n3 particles from them and to arrange them in the third box. So now see, these arrangement, or let's say this arrangement is independent of this. The third arrangement will also be independent of this. So total number of arrangements W, that is thermodynamic probability, it will be simply multiplication of all these things. That is n factorial by n minus n1 factorial into this thing multiplied by this n minus n1 factorial by n minus n1 minus n2 factorial into n2 factorial, multiplication by the next terms. See, this will be gone, and in the next case, so with this the third one for of the third term, and this quantity will be gone. So simply we will be left with n factorial divided by n1 factorial, n2 factorial, n3 factorial ni factorial, or let's say nk factorial, not I, nk factorial. So W Maxwell Boltzman is simply n factorial by I equals to 1 to k ni factorial, where this sign is the multiplication sign, just like this is summation sign, this is multiplication sign. So now we are done with what? Wait. So now we are done with the first goal. What was our first goal? Our first goal was to take n1 particles, n2 particles and nk particles from this n and to arrange them in these boxes. First goal is completed. Now I have to arrange these. Now I am having n1 particles in my hand to arrange in these cells. So now I will arrange them in the n1 particles in this cell, n2 particle in this cell, nk particle in this cell. That will be our second goal. And Maxwell Boltzman distribution, or this is valid for classical particles. Classical particles are non-interacting, right? Classical particle, they are non-interacting particles. So now I have to arrange them in the, okay, let's take the first box. Classical particles are non-interacting. So now let's take the first box. So it was having G1 cells in it, right? Total G1 cells it was having, and I have in my hands N1 particles. So how I can arrange them? For the first particle there are G1 cells, right? For the second particle, as they are non-interacting, so just from this example, see here, from this example ki 6 to the power, there are total 1 2 3 4 5 6, there are 6 levels and there are 5 particles. So level to the power particle. So similarly in this case also there are for the second particle there are G1 cells available, for third particles also G1 cells available. So for N1 particles there are G1 to the power N1 cells are available. So that is the total number of ways. So G1 to the power N1, that is the total number of ways to distribute N1 particles in these G1 cells. So now for the next cell there are, it was G2 and particles was N2. So total number of ways will be G2 to the power N2. So similarly for the kth cell it will be Gk to the power Nk. So simply the total number of ways will be, total number of ways, let's say what I can give it, let's say to PMB, total number of ways will be I equals to 1 to k, simply Gi whole to the power Ni. So this was our equation 1, this is our equation 2. Now the omega Maxwell Boltzman, that is now that Maxwell Boltzman distribution is, or it is known as total thermodynamic probability, that will be simply multiplication of this quantity and this quantity. So it will be simply n factorial I Gi whole to the power Ni by Ni the factorial. This is our Maxwell Boltzman distribution. Okay, thank you. Oh, one more thing. This is for distinguishable particle. When the particle was distinguishable. For indistinguishable particle, okay, I need to take another page. For indistinguishable particle, it will be simply omega Maxwell Boltzmann will be n factorial, the same thing, just it will be divided by 1 n factorial. So this will be the distribution function for indistinguishable particle. Now it's done.